So I would like you please to applause and welcome Mr. Alberto Del Bimbo, who just came from the University of Firenze in Italy. And he's going to talk about the learning compatible representations and large pre-trained model updatings. Thank you, Mr. Del Bimbo.
Thank you very much, Mr. Chair, and thank you all for inviting me this morning. We will give a talk on something that is not directly focused on generative AI, but we will address a more general problem. That's the problem of having an embedding model, and you want to update the embedding model, having, nevertheless, it compatible with the previous model. So the problem of updating models. So we will talk in this regard of visual search systems, where this problem particularly applies, but in the final part of the presentation, we will also show that this problem also applies when you use foundation models, the representation of foundation models, and when the foundation model is updated and you want to use the new representation still being compatible with your previous representations. Just for your information, this problem also applies for generative AI. We will not talk about that. But you know that recently you have generative AI systems where you have a RAG, Retrieval Augmented Generation, which is a case in which you want to update your generative system with a retrieval system that retrieves more recent information and makes your generative AI more powerful because more informed about the new information. We'll not talk about that, but take in mind that we talk about retrieval system, but retrieval systems are going to be joined with generative AI in the very next future. So, let's start with a review of visual search systems. Visual search systems are systems where you make a query giving some image and you want to retrieve from a gallery similar images. You see that in the right part of this slide. You have users, you have images, you have an embedding model, a deep network that creates a representation. You want to compare this representation with representation of images in a gallery set. So at the very core of the system, you have a deep network that creates representations. And you see that in the left part of the slide, where you have a training set that is used to train your deep network, and then you have a gallery images that are passed to this network to create the gallery set features. Those features that you will match with your query afterwards. So the very problem that leads to the need of compatible representation is that in the real world, you have novelties that continuously emerge. That means, for example, that you have new data, so that with new data, you want to make your network more powerful. You want to train again your network using this new data. So creating a new model is something that usually happens to give you, user, a better experience. There are also other motivations for having a new model. For example, having a different network architectures, more powerful than those originally used, or different training techniques. In all these cases, your deep network that you use to create your gallery set will be updated, need to be updated. So, what is the problem? Well, if you want to use the new model in your search retrieval system, what you should do is re-index the full gallery set, having all the images of the gallery set that are passed to the new model so that you can create new features. Otherwise, you cannot use the new model for the query. So this re-indexing of the gallery set, this creating new features with the new model, can be very costly because typically the gallery set is a huge amount of images, and recreating features for this huge amount of images can take days or weeks. Of course, there is also carbon footprint, there are storage issues, privacy issues, a lot of problem in this re-indexing of the gallery. Re-indexing of the gallery is conventionally called also backfilling. So backfilling is something that could be avoided. So the problem is how to exploit the new deep network, the deep network that has been trained with more data, which is more powerful than the original one. So this is where compatible representations came. Compatible representation means don't worry of backfilling, re-indexing the gallery set, but just create a new representation that you will use for the query, which is compatible with the old one. So in the gallery set, there will be still the features obtained with the old network, but the query features will be obtained from the new network. So that compatibility means that the new representation of the query and the old representation of the gallery can be compared. In other words, you can make the query satisfactory. This is very helpful because it avoids the re-indexing of the gallery set, preserves privacy because you don't need to have images of the gallery set still available for re-indexing, and is of course memory efficient. So this slide tries to resume what we have explained so far. This is the, let's say, not suggested way of behavior, backfilling, re-indexing the gallery. You see, you have the gallery photo collection, you have an original training set, you train an old model, the pink one, and you obtain a gallery feature collection, the pink cylinder. Then you have new embedding training set, the training set which is updated with new data. a new model which is more powerful than the old one, and you have to pass again all the images to the new model to obtain a new gallery feature collection, the blue cylinder. Then the query is passed to the new model, and the query features are matched with the new gallery. Well, this is backfilling, and typically you shouldn't do that. You should do instead using the compatible representations. That means the gallery photo collection is passed to the old model, trained with the old embedding training set. You have the gallery features, the pink cylinder. Then you have a new training set. You obtain a new model, updated, more powerful, but this new model is compatible with the old model. So you perform a training set, a training of the new model, which is compatible. We will see in the following slides how to get it. In this way, the query features obtained with the new model can be directly compared with the gallery features made with the old model. So, I hope now this concept of compatibility is clear. Now, you want to compare features obtained with a model with features compared with a different model. So the two models must be compatible, otherwise you can't compare. So in 2020, so 3.5 years ago, a team of people from Amazon defined this compatibility criterion. So a criterion according to which you can declare that two representations are compatible. And the compatibility criterion says that if you have two models, the old and the new, the phi old and phi new, and you have a pair of sample, xi and xj, then one constraint of the criterion says that if xi and xj are of the same class, then the distance between these two samples, where the representation of xi is obtained with the new model and the representation of xj is made with the old model, should be less or equal than the distance between the two made with the old model. In other words, if they are of the same class, if you use the new model must be better than the old. It's more powerful. So the distance between two samples of the same class must be less than before. Instead, if the two samples are of different classes, then the distance should be higher. That's the second criterion. So, in other words, the new model must behave better than the old one, still maintaining the constraint between samples of the same class and samples of different classes. This picture gives visually what we have said in words. If you have samples of the same class, the samples will be closer to each other if you use the new model for the query and the old model for the gallery. Instead, if you use the old model for the query and the gallery, the features should be more sparse. If the features, instead of different classes, you see that on the right part of the slide, then the new model should make them more separated than before. So, but this is a theoretical definition, because this definition implies that you verify these two constraints for all the pairs you have, of samples you have, which is unfeasible, especially if you have a lot of images. So they defined a second criterion, which they called the empirical compatibility criterion, which is the practical way in which you decide if two representations, the new and the old, are compatible or not. And the new criterion, the empirical compatibility criterion, is that consider some evaluation metric, for example, accuracy for retrieval. And then check if the accuracy you obtain when in your retrieval system, when you have the query representation obtained with the new model, the updated model, and the gallery representation obtained with the old model, check if the accuracy is higher than the accuracy you obtained when using the old model for both the query and the gallery. Still, the new model must behave better than the old one. What is important is that the query representation is obtained with the new model, but the gallery is still the same as before. You don't need to backfill all the images. So this is the criterion we will use in the following, particularly to compare different representations and check quantitatively if they are truly compatible or not. So, so far we have seen compatibility in one step. The old representation updated in the new representation. But of course, during the life of a system, you may have several updates. You know, you change the old representation because you have new data. Then afterwards, new data again to retrain the network and having even better network and so on. So you may have multiple updating steps. Of course, the criterion, the empirical criterion, also applies in this multi-step case. And this picture let you know what happens in a multi-step. You have, if you look on the right side, if you have a model, phi1, which is updated with new data. And then you have a second model, phi2. This second model, for example, could be used for the query, but matched with the features obtained with phi1. And you see the arrow in the bottom, the first one. Then the phi2 could be updated again. You get phi3, and phi3 could be used against features that were obtained by phi2, but also with features that were obtained by phi1, and so for phi4. So in other words, compatibility does not limit to the previous model, but addresses all the model during the life of the system. So we have now an animation that shows you this multi-step updating. And on the right side, in that black box, you will see a tool, let's say, that will help you practically to understand when a system when a representation is compatible or not. We will call compatibility matrix, and you will understand using this animation how it is formed. So we start with the model phi1, and then of course in this case we can only compare the query with the gallery obtained with this representation. But if phi1 is updated to phi2, then the compatibility issue occurs. In this case, of course, you can use phi2 for the query and for the gallery, but this means that you have to backfill all the gallery. We don't want to do that. Instead, we want to use the phi2 only for the query and having a phi1 for the gallery, the old representation. So you see the arrow below in this case, and you also see what happens for the matrix. For the matrix, you have the self-test, which is phi2, phi2, but also the cross-test, which is phi2, phi1. Then you update phi2, for example, with new data. You have phi3. And phi3, of course, you may use it for the gallery and for the query, the arrow on the top, but this is not what we want to do, is backfilling. Then, instead, we want that phi3 is used for the query, but we want this representation be compatible with phi2, the first arrow, but also with the phi1, the second arrow below. And you see in the compatibility matrix, you have 3 boxes, the self-test, the cross-test for compatibility with phi2, and the cross-test for compatibility with phi1. And finally, phi4, new data, again, backfilling, which is not suggested. And then instead, compatibility in the bottom towards phi3, phi2, and phi1. And you see in the compatibility matrix the self-test and the cross-tests in the bottom line. So you see that this compatibility matrix, you can fill it with the accuracy you get when you use the self-test or the cross-test. So this compatibility matrix with the accuracy values helps you to understand if the compatibility constraints are satisfied or not when you use a new representation. So now we are ready to talk about some solutions to have compatible representations. I hope we have understood so far what compatibility is and when it applies. Basically, it means that you want to align 2 representations. And we will analyze different cases when this applies. Particularly, there are 2 fundamental cases. One case is getting the new representation, retraining from scratch the network. So the new model that we use for the query has to be retrained using the original training data plus the new data at each step of updating. The other case is instead the case when, for some reason, for example, you have no more the original training data, you just want to use the new data to obtain the new model, step by step. So in this case, you just sequentially fine-tune the new model at each step, using the model you have already, and you adding to that model new data. So this is the case of continual learning. You don't retrain from scratch, but just retrain, you just fine-tune step by step. So there are two basic cases of obtaining compatible representations for the new model. Of course, the second case is a more realistic case, but also more difficult to obtain. So we will analyze both. This is what happens in a picture when you retrain the model from scratch, when you obtain the new model from scratch. And you see you have different tasks, the updating tasks. Each task has new data, that X, the arrow pointing toward the top. So task T-1 has X T-1, task T has XT, and at each task you have a training data set. So the new data sums to the training task. So you train the new model using the old training data set plus the new data at each step. So this is the first case we analyze, and we look for solutions for that. What is the issue in this case? The issue is that when you update a deep network with novel classes, the internal representation of the features changes. You have a picture of that. Here you see, for a sample case, 6 classes on your left side. You have a 2D representation of that. You have the features, which are the dots, colored. And then to these 6 classes, you insert, you add a new class, the pink one on the right. So this is updating the system with a new class, making the system to recognize a new class. And you see what happens with the old classes in this case. The old classes have a different representation in the representation space. They occupy different parts of they move in the representation space. So that means that if you compare the new representation with the old, comparison doesn't work, because they occupy different locations in the representation space. So same class, samples of the same class cannot be compared with those of the previous representation. So this is the main issue in this case, when you have the old training set and you add new data. So we are interested in having the new representation that don't change the geometrical structure in the representation space. And there are 2 ways to do that. One is learning a mapping function. You have a new representation, you have an old representation, learn how the old knowledge can be transferred to the new model. This is one approach, and you see here I listed 3 among the most important approaches for doing that. Then I will give you some references in the very last part of the presentation. The other approach is using direct comparison. So don't learn a new representation, but just make a representation which is compatible. This is the most effective approach that has some solutions so far, and you see here 4 of them. So briefly, some of these methods. This is one of the mapping-based methods. As I told you, these methods are mapping-based, so they require that you perform additional training. You take some samples from the old and the new data, and you try to learn a representation. You use several losses to do that. So you use a composition of losses to learn this new representation. You have listed here similarity loss, dual classification loss. You know, we don't go in details, should take too much time. If you are interested, look at the paper. But this is not a good way to do that. Why it's not a good way? This is explained in this slide, where we show a second method following this approach. You see here what these approaches try to do with these losses. It's basically try to make the prototypes of the classes closer to the old prototypes. So you have seen that if you have a new representation, the class prototypes move in the representation space. Well, these losses try to move them as little as possible, so to make them closer to the old ones. But what is the problem? The problem is that you learn a new representation that transfers the old query representation in the new one. So if you have multiple transfers, you know, the imprecision of this transfer multiplies. So in the very end, if you have several updating steps, you have to make the combination of several transformations. So it's very ineffective and imprecise. So in the very end, compatibility is lost, especially if you have multiple steps. So the true approach is the second. The second is direct comparison methods. That means learn a representation which is compatible, which obeys to the 2 criteria, the empirical criteria we mentioned in the beginning. And one method very successful is the one that was proposed by the people who invented the empirical criteria, compatibility criteria. This is BCT, backward compatible training. Basically, this means, okay, you have a model, which is the old query model. Well, let's freeze that model. Let's freeze the weight of the model. And then let's make the new weights, the weights of the updated model, to be as much as possible aligned with the old ones. And to do that, we use a new loss they call influence loss that try to move class prototypes closer to the previous one. So the new model, as you read here, learns from the old and the new data and try to compensate what the old representation can't do with the new data. This is using these two losses and freezing the first model. This is another approach that we believe is better than the previous, not just because we did that, but because it follows a similar but at the same time very different criterion. The goal is the same. Try to make the representation such that the class prototypes of the new model are near or the same of the old model. And we have seen that in the previous approach, the BCT, they tried to do that using losses. Using losses, they try to make these prototypes close to each other. But here we follow a different approach. And the approach is, it's possible to have fixed classifiers. Next slide will let you know what they are. Fixed classifiers are classifiers where the last part of the net is frozen, is not learned, is fixed. And then particularly, let's make this frozen part, let's make it follow a particular configuration. In other words, let's make the prototype be in specific parts of the representation space. Let's force them to be in specific directions of the representation space. And these directions are those given by the so-called regular polytopes. We will show what they are in a minute. So what are fixed classifiers? This slide probably gives you an idea of what they are. This is a deep network. In a deep network, you have a learnable transformation at the very end of the model. This is used to adjust the decision boundary of the classes. Well, let's fix this part. In other words, let's give these weights fixed values. And let's train only the part before. It has been demonstrated that doing that, the network doesn't have any loss of performance. Doing that is also helpful because, of course, this is the most costly part of the network. So if you fix, you save memory, for example, and you save computational time for training. So it's very okay having fixed classifiers. You don't lose performance and you have a lot of advantages. Why this happens? Because deep networks are expressive enough. They don't need that, mostly. So these are fixed classifiers. We will use fixed classifier. So the problem is how to fix these weights of the last part of the network. And, well, let's skip this. Doesn't work. How do we fix these weights? And this is where polytopes come. Polytopes are regular polygons. In other words, regular polygons are polygons where geometrically regular. Geometrically regular in high dimensional spaces. So, particularly, there are a very large number of these polytopes, but if your space dimension is higher than 5, you only have 3 polytopes, regular polygons, in this high dimensional space. And these are so-called D-simplex, where D is the dimension of your space, D cube, and D orthoplex. And you see in the right part of the slide how they are shown in the 3-dimensional space. So you see in 3-dimensional space, the D simplex is like a pyramid. The D cube is like a cube, and the D orthoplex is double pyramid. So why these are interesting? Because these regular polytopes, regular polygon in a high dimensional space, have the property that if we use their directions, these directions are maximally separated. In other words, they create angles that are the maximal you can obtain. So if these are the class prototypes, your class prototypes are arranged according to these polytopes, class prototypes are maximally separated. That's a very good feature because that means that your classes are very well recognizable in a retrieval system. So particularly, we want to use the D-simplex among these 3 because the D-simplex has a good property. The angles are the same for all the classes. So, resuming our approach, we fix the classifier of the deep network, so the last part of the network, and the values of the weights are obtained following the D-simplex configuration. And when you use the D-simplex, the weights are given with this formula you see here. So if you have D vertices, you can have K classes, which is K equal D plus 1. And the weights are the standard basis, which is 1, plus the last one, the last weight, is given by that formula. 1 minus square root K divided the K minus 1 multiplied by sum of the standard basis from 1 to K minus 1. So very easy. It's fixing the weights to these numbers. So in the right side, you see how the network behaves. There is one part which is trainable and one part that is fixed. The part which is fixed has weights that are given by this formula, and the part which is trainable is the rest. So if we do that, that means that prototypes of your classifier stay in fixed directions of the representation space. And this holds for the old model, but also holds for the new model. So this is the way in which the new model, the updated model, has prototypes exactly in the same directions as the old model. So we don't need anymore the losses as in the BCT approach to force the two representations to be close one to the other, because class prototypes are exactly in the same directions in the representation space by construction, because in both cases, the old model and the new model, they are constructed using the D-simplex. So they are exactly in the same approach and in the same direction. So, but when we update a model, we add new classes. So one difference between the old model and the new model is that the new model has more classes than the old. So if we have a D-simplex with a fixed D, that's a problem because, for example, the new model could need D plus something, could need more classes. So how to solve this? Simply solving that by fixing a large D that contains the classes we have so far and the future classes we don't have at this time. So that every time we update the model, the new classes just go in the free parts of the representation space. It's like we fix a large number of directions for the prototypes. We just occupy some of them. The others are free for the new classes. And in this way, the old classes still are in the same position as they were before in the old model. This is what I said, giving a picture of that. So these examples let you know how this approach works with respect to the previous approach. In the upper part of this slide, you see what happens when you have sample representation and you add new classes. You see that in this case, for example, the red class, when we insert a new class, changes its position. You can notice that in this case, but even more in this second updating step. You see that the red that initially was here, now is here. What happens if you use BCT, the direct approach with the losses? You see that BCT is slightly better than before. You know, the representation moves, but doesn't move too much. But look at what happens with the approach with the fixed classifier and the D-simplex. You see that updating the model with new classes doesn't change the position of the old classes. The red class samples remain in the same position despite the insertion of the new classes. So this picture shows you what happens in the compatibility matrix. You remember the compatibility matrix? that was used when you have several steps of updating, and you put in the boxes of the matrix the accuracy that you get at each step. And then you have the compatibility constraint that is in the right part of the slide. And you see that compatibility is assessed if you use the new model with for the query and the old model for the gallery, and it's higher than using the old model for the query and the gallery. That means that if you look at a column, the values in the column should be higher than the value that you get when you use the old model, which is the diagonal. So looking at that, you see that the red is when compatibility is not assessed. And you see that BCT doesn't assess compatibility in most of the case when you have, for example, 10 updating steps. You have red everywhere because all these values are less than the value when you use old model. You see, when you use the model number 2 for the query and the model number 1 for the gallery, so this element, this value is less than when you use model number 1 for the query and model number 1 for the gallery, which is this one. Also, when you use model number 3 for the query and model number 1 for the gallery, this one, this value is less than when you use number 1 and number 1. So this is also for the others. Instead, when you use the CORES model, the model with the fixed classifier, you see many blues. That means that in this case, it is compatible. You can see, for example, here, 0.39 using model 2 for the query and model 1 for the gallery. It's higher than model 1, which is exactly this condition for compatibility. So this difference also holds for a larger data set, like here for the Casia web data set. So you see comparison with many more other systems, and you see that the CORES is all blues, at least for 5 steps of updating, and the other are almost all red. So this confirms that if you want to have compatibility, you have to force 2 representations to be compatible. That means force prototypes to be aligned. And the very intuitive and simple way to do that is using fixed classifier, that by construction you do that. Let's skip other numbers that confirm this aspect, and let's go to the second case, which is more difficult. This is a slide that says why the second case, the case of having compatible lifelong learning representation. So in the case in which the model is continuously updated, why this is more realistic case. Because training from scratch a deep network using the old and the new data, as we have done so far, is time-consuming or unfeasible, especially if you have large models. So the most reasonable case is this one. When at each task you have your own data, xt-1, xt, for tasks t-1 and task t, but you have for the previous data just a few samples, samples that you have in some episodic memory. So you use these samples to keep memory of the past, but not the full data, just these few data in the episodic memory. So this is the case of continual learning. Continual learning, which means class incremental learning. In other words, at each step you add new class. And the step before you recognize two classes, for example, cat and dog, and then you have a new class, you want to recognize also birds. This is exactly here. The episodic memory retains cats and dogs, and you have x-1, which are birds. And you want your system still continues to recognize cats and dogs, but you also want to recognize birds. And continual learning typically follows two approaches. One is using replay or episodic memories, as in the picture before, or you use knowledge distillation. But let's give a look to the problems you have in this case, which is different from the case we have discussed so far. One problem is the same we had in the previous case. You add new classes, the representation moves. So you have to freeze the representation, otherwise it doesn't work. The other problem is that in this case, you don't have all the knowledge of the past. You just have an episodic memory. So you have the phenomenon so-called catastrophic forgetting. So the knowledge that you accumulated get lost. And this animation shows what happened. You have new data, the old knowledge drops. New data, then old knowledge drops again. New data drops again, drops again. So you have something like that. So basically, you remember the most recent data, and you forget the oldest. So you have to solve these two issues. This is what you have to do. You have several tasks. At each task, you learn new classes. But at some point, task number 3, you have new classes. You train the data using the new classes only, but you want to retrieve data where you have representation of the old and the new classes. So in this case, which is very realistic, you have few papers working on that. One is this one, which is called the CVS. Extension of the CBT approach we saw before. So they try to force the alignment of the new representation with the old one, but take into account also all the information that you have in the episodic memory, which is the information about the past. So these losses try to do that, align the new representation, the representation you obtained with the new data, those in this blue box, using also the replay data. So they use losses to make this alignment, also considering the replay embeddings. And here is how this simplex approach can be extended also to this case. The extension is just taking into consideration not only the data that are available at task T, the XT, but also the data you have in the episodic memory. And using a loss to help the system at time T, the model at time T, to be aligned to the model at time T minus 1, which is frozen. So this is the new loss. It's a combination of the D simplex, as in the previous case, plus a distillation loss that has the goal of reducing forgetting. And this is an evolution of this approach. The evolution of this approach is that starts from the consideration that when we use cross entropy, basically the cross entropy aligns the feature to the class mean. So the direction of the prototype are the mean of the classes. But when you have multiple updates, just aligning to this, to the class mean, to the first order, is not enough, because you may have a combination of updates. And this means you have higher order distortions that occur. So the idea was, well, use a loss that takes into account higher order distortions. So in other words, we used a contrastive loss, which is the one you see here. Just taking into account what happens when you have multiple updates. So this loss is much better because you see here what happens if you use the standard cross entropy and this higher order loss. And you see how the loss converges during training. You see the red is the cross entropy. Immediately goes to 0. The other is much slower. That means learns more. And learning more learns all the discrepancies that occur during updates. And you see here how this is true. You see the approaches, the BCT, for example, look at that. The CVS, the model before, they both use their losses to try to align the new representation with the old one, and the approaches using the D simplex with the feature distillation and the higher order constraint loss. And you see that in this last case, for 5 steps, you have compatibility almost everywhere. You see not compatible elements are those marked in pink. And you see that D-simplex works generally better, but the D-simplex op makes a very good work when you have multiple updates. These are numbers for those of you that want to give a closer look to them, that compare the accuracy you obtain for the different methods. And you see in bold that this latter approach is the very best. So this is the very last part of the talk. And has finally to do with large models. So what we have told so far is a general issue. Is the general issue of comparing two representations, one which is updated and one which is the old. And we have considered the case of retrieval system because this is the case where this typically happens. You have the new for the query and you have the old for the gallery. And you want just to update the query, not the gallery. And we have seen two cases. One case where you update for the query, but you reuse old and new training data. And the case in which you don't want to use the old data to retrain the new model, but just the new data with some episodic memory. But what happens with the large models? This picture gives you an idea of what happens with the large model. Because with large models, more and more, you use them to have very strong representations. They have been trained with a lot of data, so they give you very good features. So you use these large models to build your own models as a basis for your own models. You see here what happens. You have a large model, then you use it for by fine-tuning to create your own model. And then your own model is used, eventually fine-tuned, until a critical point. The critical point is when the large model is updated. Is updated by someone who is not you. And so the issue is what happens with your updatings? Because this changes the representation. So if you use this, your updates can be lost. This is why compatibility happens also in this case. Your updates will not be lost if the representation of the large model, the new representation, is still compatible with yours. If it's not, you will lose all your work. So let's talk a little bit about these foundation models. So this picture is very nice. It was given to me to one of my PhD students, and of course we don't give a look in detail to that. It's like an abstract painting, but can give you an idea of how this world is growing. And these foundation models are trained on a huge number of data. They are trained on broad tasks, and they can be intended as starting points to build specialized models. So they can be used as a zero-shot learning, but also, and more used to fine-tuning, to adapt the network to perform some target task. So this is why they have been called the foundation models. And they are really a paradigm shift in artificial intelligence. So basically, I told you in the very beginning, we will not talk about generative AI. Yeah, we'll not talk about that. But consider that these models are built on the transformer architecture. And the transformer architecture, as you know, is made of two parts, one encoder and one decoder. So look at the encoder part, the part where the representation is made. Is here that compatibility is important. Because this encoded representation, this embedding, is what we can use from the foundation model. Because it's a very powerful representation. So, and this is the part we want to be compatible, even though this is changed. Because this part can be fine-tuned for our target task, and then could be changed by the company or the entity who made the foundation model. And so we don't want to lose what we have done when we fine-tune this representation. So this is the case we discuss in the next 10 minutes. What is a solution? Solution could be, well, we have seen that D-simplex works because D-simplex tell you where the class prototypes go. We have an encoded representation. Well, let's make the large model be based on D-simplex. If that's is accepted, well, our model is D-simplex again. At sometimes the large model is updated, but it's D-simplex, no problem. We have seen before there is no problem because the prototypes are in the same directions, look at the same direction in the representation space, so we can substitute the new model seamlessly. But the problem, you see here, indeed it works. These are compatibility matrix, and you can see that if you substitute the system you had at the beginning at step 3, for example, look at these boxes here, or at step 5, so you have 2 replacements with the updated large model, no problem with the compatibility. You don't see any pink boxes in the compatibility matrix. So using D-simplex works. So you have large model built according to D-simplex. You download this large model representation. It's D-simplex, of course. You fine-tune it, remain D-simplex. Then at step 3, for example, you substitute with a new large model that comes from the company. Well, no problem, because still compatible. Again, a new replacement, still compatible, no problem at all. But what is the problem? These are, again, what happens in comparison with other performance. You see here that the simplex continuously goes up. That means that it exploits the new representation. The new representation is better than the old, so it works better. The other approaches decay. And these are quantitative elements to show that. But what is the problem? The problem is that the company could not agree to build its own system using the simplex. That's a big issue because you know, they didn't do that. They don't want to do that. They don't care doing that. So if this is the case, and this is the most common case, one problem exists. The simplex is good, but unfortunately, is not usable. So what can we do? These are the very last 3 slides. We can use knowledge distillation. Knowledge distillation is a powerful tool that allows to transfer knowledge from a large model to a smaller model. And we can use it to transfer the knowledge from a large model which is not D-simplex that has been built with a trainable classifier to a D-simplex model. And in this, so this is what we say. We have an original large model which is not D-simplex. We do it knowledge distillation. We extract knowledge, and we build a distilled model which is D-simplex. And at this point, we can use this distilled model as the surrogate of the original large model, and can use this to perform model replacement. And at this point, you wonder if doing distillation, you lose something, and how much you lose in performance. And this slide and the following show you that you can lose, like in this case, you have the teacher, which is performing on the flowers dataset on 99 performance, and you make a distillation with a fixed classifier student, and you see that 99 became 60. Of course, even if you perform a knowledge distillation with a fully learnable student model, you go around 60, less than 60 indeed. These are experiments made on visual transformer. So it was pre-trained on ImageNet 21K, and then fine-tuned on Oxford Flowers, and then distilled on a student that is trained from scratch. So the student had no knowledge at the beginning. So we can lose in this case a lot, 1/3. And this is indeed the other case. The case in which we still have a teacher, still performing 99.22, and we distill this system in a student which is fixed, the D-simplex, and a student which is fully learnable, including the last part. And you see that in this case, 99 becomes 91. So you lose, but you lose a little bit. And you lose very little because in this case, the visual transformer has been pre-trained on a small part of ImageNet, ImageNet 1K. So the conclusion is if you don't have a large model which is built according to the simplex, you can use knowledge distillation to transform into a D-simplex. You can do that with little loss of performance, and then use this surrogate model to perform seamless model replacement, because the new model representation is still compatible with the representation you had in your own model. So this concludes the presentation, which was very long, so I hope you are still alive after that. And these are a lot of references that I put in the presentation. I think you have copies of that. I gave Mohammed is the boss of our team and has all the data. So if you are interested in this problem, you can find here a number of references. I think they are quite complete. And models. But as I told you, this is also a problem for generative AI. I don't know how many of you have been aware of RAG, at Retrieval Augmented Generation. RAG is the very last invention of generative AI. Because, for example, you have seen that ChatGPT is not updated after a date. That means if you ask something about 2023, unfortunately, they are not able to give you any answer. Some other more recent systems try to do that, but RAG is a solution for that. Because RAG means have a generative system, but is coupled and trained together a retrieval system. And the retrieval system retrieves, given a query, data from a large indexed data set, retrieve data from an updated data set, and then this new data are used as prompts for query, for making the generation. So in the very last generation of generative AI, you have the generative part, but you have also the retrieval part. And as we try to explain to you, this compatibility particularly addressed the retrieval part, where you had to compare representation. And when the representation must be, for some reason, updated, and you want to exploit this update because it gives you better performance. And you want to exploit that, not losing the past. So I hope this has been useful to you all. And if you have questions, happy to answer now and afterwards until we are here. Thank you very much.
Hello, thank you very much for the presentation. I have a question about on the loss function.
Can you speak louder, please?
Hello, Ando? You hear me now?
Not well.
So my question is about the... Yeah. Ah, okay. Okay. I understand. So thank you for the presentation. My question is about the loss function that you used. Can you talk about it a little bit? How, what's the expression and how did you build it? The hyper. Yes.
The Hock loss.
Yes, the Hock loss. Please.
The Hock loss. So this Hock loss is a combination of two losses. One is the cross entropy loss, the first part, this one. Let's use this, probably better. This is the cross entropy. This is the contrastive loss, which is, can be demonstrated that this is an approximation of the KL divergence. And this takes into account how discrepancies work together. It's like a cross correlation, let's say. So, which is, you see better, wow, you see better here. So, while this is used just to keep features stable, this is used to take into consideration the past. And this is the expression. Well, going in detail, I suggest to read the paper.
Yes, okay.
Because it takes a lot.
Yeah.
But what is important is that this is like a KL divergence, something like that. That means putting together, the representation of the present with the representation of the past. But they are delta.
Okay.
The difference.
So the main idea is to keep the information from the past. Okay.
Yeah.
Thank you. Thank you.
Only consider how much the average is different from the new representation and the past. Because the cross entropy aligns features on the average of the class.
Can you repeat your question?
But you don't, if you want more, for example, not only each single class, but how do two classes compare together, then you need something like the KL divergence. And this loss takes into account that. So it's like not the first order, but higher order. That's in words, but in maths, please read the paper.
Alberto, I have one question,
sure.
general question. Thank you very, very much for this very nice talk, and there are, I think, many at the end. I have only one question about, we are working, as you know, during human machine interaction, usually we need to learn continually, because we have a new data, the past, so we have to learn. Do you think that this approach can be applied for this kind of application of human machine interaction to learn continually?
Let me think a little bit. So you say you want to learn in real time? Yeah. These kind of problems we discussed so far are not for real-time learning. They are, for retrieval systems, that means, at some time you have new data, and you want to exploit the power of this new data. So exploiting that means update your network. But update your network just for the query, not for the gallery, because for the gallery, kill. And that means that you have time to use this new data and retrain the net. So this is not real-time updating. It's offline updating. Real-time is something completely different. I don't think it can work. It takes enough to retrain a net. So I'm not sure it can work in that case, but could be nice to investigate how to arrange that. Who's Stefano? Where is Stefano? Stefano, is still alive there. Okay, good. Good. I don't know. Well, it's a big issue. It's a big issue. I don't know.
Thank you. Are there any questions? Okay.
Hello. First of all, thank you so much for this presentation. It was a collection of really interesting information. My question is about when you present the RAG models, which is the retrieval augmented generative.
Sorry?
The RAG.
No,
RAG
I don't
model.
understand.
RAG models?
RAG.
Yes, retrieval augmented generative models. Probably we made a small mistake here because when we talk about RAG models, is not the concept of they are have a direct interaction with the internet. For example, there is ChatGPT-4. He have a direct access to the internet, but he doesn't consider it as a retrieval model. By consequences, the retrieval model.
I interrupt you. Can you come here? I think I don't understand what are you saying. Can you come, please? There is some echo. No, come closer. Come, don't worry. Come. You don't make the presentation.
It's okay. When you talk about the retrievals models, like you said that they are concept of the direct dimension, which is kind of wrong. Because, for example, there is ChatGPT-4. Yes, because there's the ChatGPT-4 who have a direct interaction with the internet, but it doesn't consider as a retrieval model. I think the fact when we talk about retrieval models is the concept that the area of finding the best retrieval. Like when we see the coach of retrieval models, we're gonna find that part was talked about the fact, no, please find the best retrieval, like find the best source of information or the most correct source of information. ChatGPT-4 can give you most different information, but in general, it doesn't have the concept of find the best source information. That's why it doesn't consider as a retrieval information.
So what's the question?
The question is, what is exactly the definition of RAG models? Is it the concept that they have a direct access to the internet, or just the fact that they have the best source of information?
Concept for RAG, you say?
Yes, exactly.
The concept for RAG is that, suppose, at least, we didn't try that, of course. But seems to me that is an issue that can be investigated, because for what I have read about RAG, it seems to me that generative AI is marrying retrieval, what has not been so far. Because the current generative system are trained in a huge amount of data, but the knowledge is in the weights. It's not in a data set, it's in the weights. So, and the problem is, these weights have been updated up to some time. If you want to make them more updated, retrain the huge model with more data, which is the backfilling. The RAG is something different. It's a smart concept because they say, okay, but if you put the generative model together with the retrieval system, and the retrieval system retrieves the data you missed, the new data, from a specialized data set. That, for example, is, the data from that time of ChatGPT. I don't remember how long it is updated, 21 or something. From 21 to 24, well, we have specialized data from that time on. Well, retrieve them, and then what you retrieve, use as a prompt, as a context, let's say, of the original prompt. So they enlarge the context, making retrieval. That's important because now you have a system which is made of two parts, the generative part and the retrieval part. The retrieval part has the same problems as we discussed so far. So you could want to have your retrieval part still compatible with the previous retrieval part. And this is why what we have discussed, probably, I don't say sure, I didn't test, But I believe that the problems that you have in retrieval, you may have in the next future in the generative AI. That's all.
Any other questions? So thank you, Professor Bim. Thank you very much.